Welcome back. We'll be going into the second chapter, or in your textbook is chapter 13. Yeah, chapter 13, kinetics of a particle, force and acceleration. Yeah. So the first part of the chapter will be looking at Newton's law of motion, equation of motion for a system of particle. Remember the first few chapters we'll be looking at only particle. Yeah, particle. So this is the first one that we'll be looking, first chapter that we'll be looking at the kinetics, which is we're going to look at F equals to ma. Yeah. Okay. So today's objective, student should be able to write equations of motion for an accelerating body, draw a free body diagram and kinetic diagram for an accelerating body. Yeah. Okay, example, applications. The applications is actually, there's so many applications in real life, yeah, because anything that's in motion, yeah, where you have acceleration, where it involves force, yeah, that's where you can apply these lessons to. A few examples as given in the slides are like example, this parachutist relies on the atmospheric drag resistance for her parachute to limit her velocity. Yeah, and then we have another example here. The baggage truck A tows the cart B and cart C. So if we know the frictional force developed by the driving vehicles of the truck, could we determine the acceleration of the truck? Yes, isn't it? Yeah. Okay. How? That is what I'm going to lecture you shortly. And then we also have applications in the freight, elevator. Yeah, in the previous chapter, we studied on how to find the velocity and accelerations of the based from the length, isn't it? Length equals to SA, plus SB. Remember what we did last class here? So that can be also applicable here. Okay. So Newton's law of motion. So we have three laws. The first law, a particle originally at rest or moving in a straight line at constant velocity will remain in its state if the resultant force acting on the particle is zero. So that was the first law. Now second law. If a resultant force on the particle is not zero, the particle experiences an acceleration in the same direction as the resultant force. This acceleration has a magnitude proportional to the resultant force. And the third law, mutual forces of action and reaction between two particles are opposite and collinear. Yeah, so every action has a reaction. That's your third law. Okay, your second law associates more of your force equals to ma. Yeah. Okay, now you this is the second law. This is what we are going to explain now. F equals to ma. Yeah. Next we have the Newton's law of gravitational attraction. F equals to gmm over r square. G is a universal constant gravitation and m mass. Yeah, two objects mass where they actually have mutually attractive gravitational force between them. You see, any object at all has got a mutual attraction, but it's just that the force is actually weak. Yeah, that's the reason why we don't feel the force pulling each other. Whereas for planets, yeah, the planet's mass is actually very big. So when a very big mass multiplied with a very huge mass, what happens is that, yeah, the value, the power, the value, let's say power of 34 multiplied with power of 42, example. So what happens? The power becomes big. So multiply with gravitational constant, which is 10 power of negative 11. So this value becomes still, like a value, like it has a value. Like, okay, example, okay. Well, what do you have here? For 34 plus 42, that would be 676. Minus with 11. So you still have like what? 65, 10 power of 65. Let's say you take my mass, which is power of 1, multiply with power of 1, your mass. Yeah, it means your mass and my mass, power of 1, 10 power of 1. It's just 10 power of 2. Multiply 10 power of negative 11. That's the reason why we don't have any attraction. Like you don't cling to me or I don't cling to you. Like otherwise, like planets, then yes. That is why the sun is the what you call the moon is attracted to the earth and the earth is attracted to the sun. Yeah, because of this force here. Yeah, mutual attraction between two bodies. Yeah. Okay. So like Earth, we human 10 power of 1, right? Yeah, with the Earth's planet, which is I'm not sure 10 power of what. So it's a big value, right? Earth's mass is a big value. That's the reason why we are attracted to the Earth. Yeah. Okay. So next, mass and weight. So you know what's mass, right? It's an absolute property of a body, whereas the weight is an acceleration that you have taken the mass multiplied with the gravity. Yeah. Okay. So SI unit, we only look at SI unit. For mass it is kilogram, and for force it is Newton. Yeah, Newton. Force is Newton. Okay. So your weight is a form of force, because weight is equals to mg. Yeah, mass times gravitational force. So it is actually a force. Okay. Let's move on. Equation of motion. So the motion of particle is governed by the Newton's second law relating to the unbalanced forces of the particles in acceleration. If more than one force acts on the particle, then we have Fr equals to ma. So what is Fr? Fr is the resultant force. What is the resultant force? It's not one force, but it's a summation of few forces. Okay, summation of few forces. So the first step is actually to draw the free body diagram, yeah, to show all the forces as acting, and then you need to draw the kinetic diagram. So in this question you need to draw two diagrams. One is diagram of to show all the forces as acting on the body, and the next one is the kinetic diagram. Yeah, I will go through an example. Yeah, I will repeat back the same thing, that what are the two diagrams that you need to draw. They are very important, because otherwise you will not get full marks in the exam. Yeah. Okay, so now next, initial frame of reference. This equation of motion is valid only when acceleration is measured in Newtonian or with the initial frame of reference. What does it mean? For a problem concerned with motions at near the Earth's surface, we typically assume the initial frame is fixed to the Earth. It's like a reference point. Now you always must have a reference point. Where are you referring to? Which object are you referring to? So coordinates, mostly the coordinate will be 0, 0. That is your initial reference frame. Yeah. Okay. Now also we have got internal forces and external forces. Okay. So by right, when you write your summation of forces, you have got MAI internal and MAI external. But most of the time, because they cancel off each other, the internal forces cancel off each other, so we don't consider Fi. We only look at F, the big F. Yeah. Okay. So what is you'll be seeing some terms here. Ag. Yeah. Ag. What does it mean by Ag? That all the concentration of mass is actually at the center of mass. Center of mass. Yeah. Center of mass. So in an object, yeah, if it's, let's say it's not balanced, so the center of mass can be lopsided. Yeah. But if let's say it's a very balanced mass, then like for a square, it is right in the middle. Yeah. So if they didn't mention that the mass is the mass is not evenly balanced, then it may not, the G may not be even in the center. So you have to be careful with the question itself. Yeah. Okay. So the key points, important key points to solve these questions. So we have Newton's second law. It's the law of nature. Okay, experimentally proven, not results in of an analytical proof. And then we have mass, yeah, as a measure of resistance to a change in velocity. We have weight, depends on the local gravitational field. Most of the time it is 9.81. And unbalanced forces, that causes the acceleration of objects. This condition is fundamental to all the dynamics problem. Okay, so these are the key points. And what is the procedure? First, you need to define where is your initial coordinate, where is your reference, yeah, where is your reference point. Okay, 1 second. Yeah, the first part is to actually define where is your reference point. Next step is to always draw your free body diagram. This is really very important, and show all the external forces. And then you need to draw the kinetic diagram. Yeah, kinetic diagram. I'm going to show some example later. So this 2 carries marks. Yeah, it's very important. And then only you write your equation of motion. Yeah, so these are the steps that's involved. And of course the last part is to apply the kinetic relations to generate additional equations so that you can solve. So we're going to go into an example. So in this I'll be skipping the example that is in the lecture note, because the example is a bit easy. Yeah, so I'll be going into something which is more complicated. I'm going to come to this later. So let's just go to an example now. Okay, so let's look at this example. So I'm picking this example from page 122 of your textbook, example 13.1. Yeah, example 13.1. Okay, so a 50 kilogram crate, as shown here, rests on a horizontal surface for which the coefficient of kinetic friction mu k is actually 0.3. Yeah, so the mu k is 0.3. Yeah, so if the crate is subjected to 400 Newton towing force as shown, determine the velocity of the crate in 3 seconds starting from rest. So what's the hint here? Starting from rest, initial velocity is actually 0. So there's key point here. Now remember, what is the first step? Yeah, you always must remember the first step in solving when you get this question. What is the first step? We discussed just now, right? Okay, let's just rewind and play. What is the first step? Okay, let me look at this. Okay, so you need to define the initial coordinate system, then you draw the free body diagram. Okay, let's look at this. Okay, so in this case, you just have to take the reference as your crate itself. So the two things that you need to draw is, one is the free body diagram with all the forces, and the second one that you need to draw is the kinetics diagram. Yeah, kinetics diagram. Can you see? Free body diagram which shows all the external forces, and kinetic diagram which shows the movement. So in this case, the movement is very simple. The whole box is actually accelerating in the right direction, in the x positive direction. That's it. Okay, next step is to write the appropriate equations. Yeah, equations of motion. So this is the step. Now remember, you also defined the positive and the negative directions for the forces. That is very, very important. Yeah. Okay, can you see, like example here, they are taking x positive to the right as positive, and for y taking up as positive. This is very, very important to define them. Yeah. Okay, now once you have drawn all the free forces, okay, look at this question here. You have a crate, so you copy the crate. Okay, and then you have the weight, yeah, which is right in the middle here, 490.5, and then you have the friction. Yeah, you have to write here friction, and of course you have the normal contact force that comes in a package, and then we have the 400 Newton here with an angle of 30. So copy that back. Okay, now the first equation, F equals to max. So you have to look at all the forces that is in x direction. So what do you have here? You have 1, you have 2, oh no, this is a big offense to choose that. Okay, you have 1, and then you have this 400 which can be resolved to x-axis, right? So write this down, negative 0.3 NC. Why is it negative? Because it's actually pointing to the left, which is opposite of the positive direction that you have taken. Now why 400 cos 30? Okay, 400 cos 30, you resolve it to the x direction, you get 400 cos 30 equals to 50A. Now how did you get to this value then? Okay, look at this. At the end of the day, you have an A direction, you have acceleration which is in the x direction. That's the reason why this is MA. What is the mass? 50. What is the acceleration? You don't know, but it's in x direction, right? So that's the reason why you have to write all this. Okay, so settle this part. Next, you look at y. Okay, so what do you have here? We have NC, we have this flare, possibly can be resolved into y direction, and then we have this 490 pointing down, negative, NC pointing up, positive, 400 sine 30. This is this component here, which is equivalent to 0. Now why is this equivalent to 0? Let's look at this. In this direction, in this what you call free body diagram, they have only defined that the acceleration at the end of the day is actually pointing to the right, positive of x direction. There's no movement in the y direction, no movement. Therefore, that's the reason why this thing has been taken as 0. Okay, got it? So now you solve this simultaneous. Yeah, solving this simultaneous is maths part. You should be good in maths by now. So you get your NC and you get your A value. Okay, so we are not solving the question yet because the last part of the question is determine the velocity in 3 seconds and if it's starting at rest. So you have your A. Okay, so you need to find the velocity So from the formula of v equals to u plus at, okay, your initial velocity is 0, given as a hint as rest. Rest means initial is 0. And then you have your acceleration, multiply with the time, you get the answer as 15.6. So this is how the diagram will look like. Yeah, okay, can you see this? Yeah. Important, yeah, this is equivalent to this. Okay, this is equivalent, this part is equivalent to this part. Okay, let me just erase that everything. Okay, I give you in color code so that you understand what does the diagram actually means. Yeah, okay, I'm going to use 2 colors here. Now this portion is the forces, this portion is all the forces. Can you see all the forces? Now this portion is the kinetics. See, can you see? Yeah, this is the kinetics. So that is the difference between them. So you need to actually show this and you need to show this for marks. This is what shown here. Okay, so with that, so I've completed the first part of chapter 13. Yeah, meet you in the next video. Thank you.